Hi, everyone. I'd like to thank you all for coming to the SETI Institute Colloquium Series. I'd like to encourage you to take your seats, and we'll get started here. So today's talk is by Joanne Hewett, who's from Stanford and SLAC. Before we start in with today's speaker, let me just give you a couple of programmatic announcements about this series. We have this lunchtime colloquium series every Wednesday at noon. We have a variety of speakers on topics ranging from spanning the whole gamut of astrobiology, which is our focus here at the SETI Institute. And I hope you enjoy this week's talk. Let me just give you a promo for next week's talk, which should be really interesting. It's by Margaret Race and Rocco Mancinelli, and they will give you a progress report from a workshop that's going to be here next week about developing a roadmap of astrobiology societal issues. So that should be a very interesting talk. I encourage you all to come to that. These talks are all recorded. They're videotaped. So if you miss a talk, you can always get it on our website. There's a time lag of a week or two before we get talks up usually. And so you can always go to the Colloquium homepage. Just go to www.seti.org and click on the picture of Frank Drake. You'll see there's something that says Scientific Lectures with a picture of Frank. If you click there, you'll get to the Colloquium homepage where you can see a schedule of upcoming talks. You can see archives of previous talks. You can download the presentations that they gave, and for most of them, you can also download a video. So you can watch from the comfort of your own computer if you happen to miss one of these. So since these talks are recorded, after the talk, I'd like to encourage you to hold your questions until the end of the talk. If you ask questions during the talk itself, then your voice won't be captured on the audio, and so there's a gap in the videos that's a little bit awkward. So if you wait till the end of the talk, wait till I come around and give you this microphone, and that'll capture your voice so it can get recorded for posterity with your question. And so today's talk is by Joanne Hewett, who is a professor at the SLAC National Accelerator Laboratory at Stanford University. And Joanne did her degrees, both her undergraduate and graduate work in physics and math at Iowa State University, and she's been a professor at SLAC and Stanford since 1994. So it's my pleasure to welcome Joanne.
Thank you. It's a pleasure to be here. I think everybody in the outside world is very curious about the SETI Institute and wishes you all the best of luck in finding something. So today I'm going to talk about extra dimensions. And in the beginning, men and women walked out of their caves and looked up at the sky and had many questions that they wondered. What's the world made of? What holds the world together? Where did we come from? Is there extra life out there? But since then, our thinking has evolved. But we still basically ask the same questions, okay? The only difference is we have slightly refined questions because of all of the experiment and data and knowledge that we've gained since the cave person days. So a few years ago, a panel was created and they delineated what were the most pressing questions in fundamental physics. And by fundamental physics, I mean particle physics, high energy physics, or early universe cosmology. And they listed the top 9 questions, not 10 but 9. And question number 3 was, are there extra dimensions of space? So this is one of the pressing issues that we have in front of us. And one reason it's so pressing is because we have a number of theories that actually predict extra dimensions of space. And recently, there's theories that predict that there's extra dimensions of space at a size or a scale that can be probed in present-day experiment. And so that's mainly what I'm going to talk about here. But first, I realize this is a rather diverse audience and everybody is a scientist in different areas. So I'm really going to start at a very basic level to make sure we're all on the same page. And I'm going to start with, oh, sorry, I forgot my joke. This is what people normally think of when they think of extra dimensions, right? I think of a time and relative dimensions in space or something. But no, what I'm going to talk about today is real science, okay? And to make sure that we're all on the same page before we talk about extra dimensions, I think we all have to make sure we have a firm grasp of what a dimension is, okay? So that's the first thing to define. And one way to think of it is traveling in a car, okay? So if you have a one-dimensional space and you're in Republican City, Nebraska, and you want to leave Republican City, Nebraska, as one might want to do, you either have to go west or east, left or right. You can't go north or south. There's no road in that direction. Okay, so this is a pretty good example of a one-dimensional space. For a two-dimensional space, just think of any downtown city grid, okay? Now, besides going left and right, you can go up and down. So you can move your car east, west, north, south on a grid. But if anyone's driven around San Francisco, as we all have, we understand that it's actually a three-dimensional space because there's up and down as well, okay? So these are the three perpendicular dimensions that describe all points in our three-dimensional space. So again, a one-dimensional space, you would describe a point by its location along that line called x. A two-dimensional space, you describe its location by a point with some value of x and some value of y. A three-dimensional space, which is what we have, you can describe the point by a value of x, a value of y, and a value of z. That's the same as our camera guy here, okay? You can describe his position relative to this podium by some value of x, y, and z. All points in our world, in our universe, can be described by these three coordinates. This is known as a Cartesian coordinate after René Descartes, that all points in the three-dimensional space are represented mathematically by these coordinates x, y, and z. Descartes has his picture on the old 100 franc note from France, showing that in other cultures they definitely honor their scientists and put them on the money. Here in the US, we put them on stadium cups. Here's a René Descartes stadium cup that you can actually buy off the web. Okay, so using Cartesian coordinates, we can describe geometrical shapes. Anybody who's had high school algebra knows that a circle is described as x squared plus y squared equals 1. Okay, that's a circle of radius 1. A sphere of unit radius is x squared plus y squared plus z squared. The sphere is three-dimensional, and so it has all three coordinates with it. If you had a hypersphere, okay, a four-dimensional sphere, which is something that's very difficult to draw, then you would just add in a fourth dimensional coordinate. So you have x squared plus y squared plus z squared plus w squared equals 1. And there is a fourth dimension, and that is time. Okay? So Einstein realized back around 100 years ago that time was required by relativity to be a dimension in itself. It's also required, if you think about it, along with the three spatial dimensions to specify the location of an event. Our camera guy is sitting here at a specific value of x, y, and z at a particular time. Okay? So you need time as the fourth dimension to specify an event. The problem with time, and what I've got, there's this really cool website where you can take this picture of Einstein and write literally anything on the blackboard with his handwriting, okay? So, so this is not actually what was on there, but this is known as the metric, okay? This is a metric which describes a particular point in space-time, and it depends upon the three Cartesian coordinates, x, y, and z, as well as time. Now the issue here is that time has different dimensions in the spatial coordinates. Time is in seconds. Spatial coordinates are in meters, kilometers, whatever, okay? And so what you need is the universal constant c, which relates measurements of space to measurements of time, okay? And this is the value of c in miles per hour. It's 3 times 10 to the 8th kilometers per second. And it was Hermann Minkowski that figured this out and related time to the Cartesian coordinates via this universal constant c. C is just the speed of light. Okay? And along this time in the early 1900s, these thoughts of having extra dimensions and time being a fourth dimension actually hit all of society, just like the work that you do at SETI here is hitting all people in society. And in particular, it hit the artist world with the new cubism. And this is just the famous picture, Nude Descending a Staircase, which is supposed to illustrate the concept of time as a dimension. Okay. So we have 4 dimensions. Is there a 5th dimension? Well, a Finnish physicist, Gunnar Nordström, showed in 1914 that you could unify the 2 fundamental forces that they knew of at the time, which is gravity and electromagnetism, in a single theory if you added 1 extra dimension and had 5 dimensions. Cool idea. However, this theory incorporated Nordström's theory of gravity and not Einstein's theory of gravity. The 2 were in competition at the time, and it was basically ignored. Fast forward to 1919, and Theodore Kaluza showed that gravity and electromagnetism could be unified if you added an extra dimension, only this time he used Einstein's theory of gravity. And Einstein has this quote here saying, at first glance, I like your idea tremendously. So this idea took off. So this is the first instance in which scientists used an extra dimension to solve a physical problem. Here they wanted to unify the 2 fundamental forces that existed in nature that they knew about at that time. The key is that all of these guys assume that the 5th dimension wasn't real. Okay? They assume that because we don't see it, it's just a mathematical trick. It's just a pretty way of writing an equation on a paper, but it didn't actually correspond to a real physical extra dimension. It's also worth recalling that in the same time frame, 1905, some scientists didn't believe that the atom existed either because we couldn't see it. Okay? So in 1926, when we really knew atoms were real, and we knew that things that we can't see could possibly be real, Oscar Klein proposed that the 5th dimension was real, but it was just too tiny to be observed. So he used Kaluza's theory of unifying gravity and electromagnetism and computed that in order to do this, the size of the extra dimension had to be 10 to the minus 29 centimeters. Really, really small. And that's why we couldn't see it. Okay? And again, this paper received great accolades, and the quote from Einstein is that Klein's paper is beautiful and impressive. So this is the first time that people started to think of extra dimensions as being real, as actually existing. So the unification of the forces is one of the fundamental goals that we're trying to achieve in particle physics. And in the 1860s, Maxwell unified the electric and magnetic forces into a single force, electromagnetism, and today we try to unify all of the known forces. So the strength of how do you unify a force? What does that mean? When we say that, we mean that each interaction, okay, corresponds to a force, has a strength, okay? Gravity, the interaction that we have with the planet, has a strength associated with it. The strength of a force, it turns out, is not a constant, but it runs at energy. So depending upon which energy you're measuring the interaction of that force, it has a different strength. This is a schematic representation of 3 of the forces and how they run with energy. And if they're unified, the hope is that at some high energy scale, they meet and become one force or have one single interaction strength. We know this is true for 2 of the fundamental forces. The electromagnetic force and the weak force have been shown to unify at a particular energy scale. And this is a beautiful experiment done at an electron-proton collider in Hamburg, Germany. Okay? So this has been very well demonstrated. Here is a picture of the 4 fundamental forces that we know of today: electromagnetic, weak, strong, and gravity. Here's where we are currently probing, just right at the unification of electromagnetic and weak. And the hope is that at some point, the strong force will unify, and then again at some point, will unify with gravity. Okay? And this is just to emphasize that the point that we're probing now is right here, right where electromagnetic and the weak force have unified. That's the energy scale at which we've been able to probe the universe. So, go back a minute. There's a problem. There's two big questions here. One is, when does gravity unify? Okay. We've shown this schematically. We're only probing energy scales here. Okay. So in this parlance, this is at something called a TeV scale, or 10 to the 12th electron volts, tera scale. And gravity doesn't come in and unify until 10 to the 16 TeV. So 16 orders of magnitude above what we're currently probing with experiment. And one big question is that actually what happens? Okay? This is just taking the strength of gravity that we measure at the TeV scale and below, okay, and just extrapolating and to see when it would hit the strength of the other forces. And that's at 10 to the 16 GeV. But is that what actually happens? Who knows? We're just postulating over 16 orders of magnitude of what could possibly happen. The other big question in front of us today is, what breaks this electroweak force? Okay. So one theory of gravity is string theory. You all have probably read articles, popular articles about string theory. And one of the main propositions of string theory is that all elementary particles are not actually particles, but are small microscopic strings. So, for example, an electron is not a point particle. We are currently measuring it at distances of 10 to the minus 15 centimeters, and at distances on that scale, it is a point particle. It has no structure. But string theory predicts that if you could measure it at distances of 10 to the minus 33 centimeters, then you would no longer see a point particle, but you would see a loop of string. Okay? And it's the vibrations of this loop of string that reproduce all of the known elementary particles that we see around us in the universe today. So this is one of the basic principles of string theory. This works if and only if there are extra dimensions of space. String theory doesn't make sense unless you have extra dimensions of space. Not time, just space. So string theory predicts the existence of extra dimensions of space, and it's more specific than that. In order for it to have all the mathematical properties that it should have and be well behaved, then string theory predicts that there are either 6 or 7 extra dimensions of space, for a total of 10 or 11 total dimensions. Okay? So this is pretty cool. We've got a theory that describes gravity, and it's predicting extra dimensions of space. The only thing here is, remember the size at which the point particle became strings, okay, or where you could see the fact, resolve the fact that it was a string, 10 to the minus 33 centimeters, okay? And this is the distances that we're able to probe today, 10 to the minus 15 centimeters. So this is an 18 order of magnitude difference. And these extra dimensions of space are associated with the size of the string scale here. So they're 18 orders of magnitude smaller than what we could probe today. So this is a radical idea. Sorry. Okay. So that's the old string theory, if you like, and is still a lot of work being done on that. But about 10 years ago, the radical idea came into place that perhaps the extra dimensions aren't that small, okay? That they're actually a bit larger than that. And it came about by answering the question, why is the strength of gravity this much weaker, 10 to the 33, times the other forces, okay? And the answer that these people who came up with these theories thought of is perhaps gravity is strong, actually, but it only appears weak to us. If there is a space-time, a higher dimensional space-time, and gravity freely propagates throughout the entire space-time, but we're confined to only one very small sliver of that space-time, we only see a very small part of the gravitational force because we're only a very small part of this huge space. Okay? So, the idea, just to repeat, is saying that gravity moves through the entire higher dimensional space-time and spreads out, and it spends very little time in our 3+1 dimensional universe. Well, if you do the math, okay, given this hypothesis, you find out that the extra dimensions could be as large as basically 0.1 millimeter, okay? That's not that small. That's something that we could actually have a chance of measuring in the laboratory. And moreover, these theories could be responsible for breaking the electroweak force. There's very technical ways of doing it, but these new theories not only answered the question of why gravity appears so weak to us, but it also gave us ideas for breaking the electroweak force, the symmetry. So this is due to a new generation of scientists, including one at Stanford, Savas Dimopoulos, and Nima, who was at SLAC as a postdoc when he proposed this particular theory. It remains to be seen whether or not, if this is right, someday maybe we'll have coffee cups with Nima's picture on it. This guy is a complete coffee addict. He drinks like 20, 30 cups a day, so it would definitely be a coffee cup. So these extra dimensions, in the 10 years since these theories have been proposed, we've done a lot of work on them, and we found out that they're actually extremely useful. They can answer a lot of the fundamental questions. In fact, that list of fundamental questions that I showed at the beginning of the talk can be answered by these new theories with large extra dimensions. They can unify the forces, they can explain why gravity is weak, they can break the electroweak symmetry, they can explain dark matter, which is this mysterious matter that comprises 25% of our universe, and we don't know what it is. They can explain dark energy, which is this mysterious force which makes up 70% of the universe, and we don't know what it is. It can explain the observed fermion masses, and it can explain why neutrino masses are so small, and on, okay? So these extra dimensional theories have really become very popular because they can answer a lot of our fundamental questions. All we need to do is find them, okay? See if that's what nature has chosen. Okay, so what is an extra dimension? Well, it's very difficult to visualize extra dimensions of space because we're stuck in our three-dimensional world. One way of looking at it is looking at the shadows of higher dimensional objects. Okay. So this is a two-dimensional shadow of a rotating cube. Okay, so here's your three-dimensional cube rotating in space, and if you project its shadow onto a plane, a two-dimensional plane, this is what it would look like. Okay. I remember when I was little growing up and watching Carl Sagan's TV shows, he had this Flatlander episode, and this in particular is exactly what he meant in this Flatlander episode. Well, we can do the same thing. Imagine what a three-dimensional shadow of a four-dimensional rotating hypercube would look like, and it would look like this. And I don't know about you, but these pictures actually don't really do much for me. I really don't really get the idea of what an extra dimension would look like from that. So here's another picture. Extra dimensions for us are too small to observe because they're curled up and compact, okay? Even if they're millimeter size, they're still curled up, or sub-millimeter, they're still curled up and compact. And one way to think about that is to think of a tightrope walker on one of the cables of the Golden Gate Bridge, okay? Now, if you're this guy walking on this cable, you've only got one dimension that you're, well, maybe more than one. You're aware of back and forth and up and down, okay? In particular, you're aware of down, okay? But you're really concentrating on back and forth. The dimension that you're not aware of at all is the fact that this cable you're walking on has a radius. Okay? You're not really aware of that. However, because it's a lot smaller than you are walking on it. However, if you're an ant crawling around on this cable, this circular or radial dimension is part of your physical world because you're smaller than this dimension. So you see this extra dimension. You can crawl around on the cable this way as well as back and forth. Whereas the guy can only walk back and forth. He can't see or can't move in this other dimension. Okay? So thinking of it this way, then every single point in space-time has an extra dimension associated with it, or at least one, maybe more, and they're curled up. Okay? So if there's one extra dimension, then every point in space-time has a circle associated with it. That's the extra dimension curled up and compact. Two extra dimensions, and every point in space-time has a sphere associated with it. The extra dimensions being, again, curled up and compact. 6 extra dimensions, well, then it gets very complicated, and it's something called a Calabi-Yau space, and this is what artists think a Calabi-Yau space would look like. Okay? But the point is that with 6 extra dimensions, which is one of the predictions of superstring theory, you would have these 6 extra dimensions curled up and compact associated with every point in space-time. Just like here, at every point along this bridge, you have the circle associated with it going around the cable. Okay? But that's the dimension that our tightrope walker can't perceive. Okay. There's one more way of thinking about this, and this picture is known as the brain world scenario. Okay? So this is what I was talking about earlier, that we are trapped on a 3-dimensional spatial membrane, okay? And we can't move in this higher dimensional space. So we could have extra dimensions all around us, but because we're trapped on this membrane, 3-dimensional membrane, okay, we can't perceive the fact that there's other dimensions that are orthogonal to our 3 dimensions. In this scenario, the extra dimensions don't have a restriction on their size. They can either be very big or very small. Okay? There's no restriction in this scenario. And there's theories that run the gambit. Okay? We can come up with consistent theories for either very big or even infinite spaces. And the reason we can't perceive it is because we're trapped in our brain, in our 3-dimensional membrane. We can't go off of this membrane. So, particles in extra dimensions. I've talked about gravity propagating in this full higher dimensional space-time. How do we describe that mathematically? Well, let's go back to Einstein and his blackboard. Here's E equals mc squared. This is a famous formula, but it's incomplete. Okay? This is for a particle at rest. If you have a particle that's moving, okay, then you have to put in the momentum of that particle in with this formula. Okay? So for a particle in motion with momentum p, where p is a momentum in all 3 spatial dimensions, this is what this formula looks like. Okay? You have a term for each of the 3 dimensions that the particle has a momentum in, plus its mass term. Okay? Now, clues of Klein particles are what we call particles that propagate in the extra dimensions. And we call them this after Mr. Kaluza and Klein, who first postulated extra dimensions. So let's imagine a particle moving in a single extra dimension. So here's our circles, our extra dimension, and it has a radius r. So we say that extra dimension has a size r. Okay? And if this particle is moving along this circle, then it has a momentum in this extra dimension, and it has a momentum from its motion. This is a famous problem in quantum mechanics. For those of you who have had just the basic undergraduate quantum mechanics course, this is particle in a box. Okay? You've got a particle that's moving along, but it's confined to a particular range of space. Okay? Here it's not a box, it's a circle, but it's the same thing. And what quantum mechanics teaches us is when you have a particle whose motion is confined to a defined space, then its energy and its momentum are discrete. Okay? They're discrete. There's different levels of energy and momentum that it might have. and it's related to the size of the space that it's confined in. So this is what quantum mechanics tells us. That's just solving the Schrodinger equation for particle in a box, for those of you who have had that. So for this particular case, where we have one extra dimension with a circle, the momentum associated with this is in the multiples of 1 over the radius, okay? 1 over r. So the extra momentum is some level n, where here's the discrete part from quantum mechanics. It's some level, 0, 1, 12, whatever, divided by r. So we go back to Einstein's equation. If we have a particle that can move in the extra dimensions as well as our dimensions, okay, then we have to put this extra momentum in here, right? We have to put in the components of all the components of its momentum. So you have to put in the three-dimensional components as well as the extra component, okay? So if you just stand back and stare at this equation for a minute, with a four-dimensional lens on, okay, thinking here we are in our 3 + 1 dimensional universe, this extra term to us is going to be lumped with this guy, and it's going to look like a mass, right? So if we can see this particle in our three-dimensional space, and it can propagate throughout the whole thing, we're going to measure its three-dimensional momentum plus an extra bit. And this extra bit is going to look like a mass to us. That's the key point here. So what we have is a tower of massive particles. Okay, because remember that the extra dimensional momentum is n over r. N is basically how many times it's gone around its circle. Okay, so if n equals 1, we've got our first particle in the tower that has a mass of 1 over r in our world. Okay. And then there's another particle that has a mass of 2 over r in our world, 3 over r, 4 over r, and so forth. And so what we have is a tower of massive particles that are evenly spaced in this case. Okay? Each particle has a mass with 1 over r spaced one on top of each other. The size of this spacing depends upon the radius of the extra dimension. Okay, so a small extra dimension will have a large 1 over r, and so you'll have very well separated Klein particles. A large radius will have a very small 1 over r, and so you'll have finely separated Klein particles. Okay, so this is key. These Klein particles, it's a tower of massive particles, just comes about from the fact that the momentum the particle has in the extra dimension looks like a mass to us. Okay. So Klein particles, just like the SETI Institute, capture the imagination of the world. And here's an artist's rendition of what a Klein particle looks like. This is actually hanging in the halls at SLAC. And what's amazing is that the artist's name is Don Meson, and a meson is the name of a particle. Okay, so anyway. So this is the key thing right here, is that the observation of this tower of particles is the experimental evidence for extra dimensions. Okay? Measurement of the properties of these particles reveals the properties of the extra dimensions. Okay? I already showed you that the spacing here tells you the size of the extra dimensions. So if you can measure a few of these particles, if you have enough energy in your accelerator, if you like, and you can create these particles, and you can measure a few of them, okay, then you can see what the spacing or the size of the extra dimensions are. Okay. Once you find these things, then there's a whole list of things we're going to want to know. How many extra dimensions are there? How big are they? What's their shape? What particles feel their presence? Do we live on this membrane thing or not? And the important thing is that all of these things can be answered by measuring the properties of the Klein particles in experiment. We might have some other questions as well, like can we park in these extra dimensions, or is that where the extra socks go? These are the kinds of things we can't measure in an experiment. We'll just have to find that out some other way. Okay. And again, just a way to think about how we can observe the properties of these extra dimensions. A good analogy is animal tracks. Okay? So skilled animal trackers can determine the size or the type of the animal, the speed it was going at, or the animal was injured without direct observation of the actual animal. I mean, this is something that we're all very familiar with. And this holds true even if the animal is extinct. Okay? And we've never seen one of these animals. Well, it's the same type of thing with extra dimensions. Even though we can't see them directly, by measuring these Klein particles, we're going to be able to determine everything about them. Okay, so there's 3 ways that we hope to see extra dimensions. Number 1 is modification of gravity at short distances. Number 2 is the effect of these Klein particles on astrophysical or cosmological observations. And number 3 is the observation of these Klein particles in a high-energy accelerator. This one, number 3, where you actually have the direct observation and you've got the particle in your experiment in the laboratory, affords you the most information, okay? But you have to observe it, and you're limited by the energy of your collider, so that you're limited as to the size of the extra dimension you can probe because you're limited by the energy of your collider. Whereas number 2 in particular, you're limited by the energy out there in the universe, so you can actually probe much smaller distances, but you can't really, if you saw something, you couldn't nail down what it was or nail down the properties of the particles. Okay, so I'm going to discuss each one of these in turn, and then that'll be it. Okay, so modifications of Newtonian gravity. Well, as we all know, Newton was sitting under his apple tree and saw that the force between the apple and the earth was given by this expression here, where the key here is that the force, okay, gravitational force, goes as 1 over r squared, okay, where r is the distance between the 2 objects that the force is acting on. So here it's the distance between the apple and the earth. The constant out front is actually not a constant. It runs with energy, okay? It's a constant at a particular energy. Because it's gravity, it runs very slowly, okay? So that's why we don't see it and see that change in our everyday world, but it's not actually a constant. For this, Newton got himself on the money, okay? So modifications of Newtonian gravity depends upon your size compared to the extra dimension, okay? So this inverse square law of gravity is modified with extra dimensions, provided that either you or your apparatus is small enough to detect it. So here's an example with 2 extra dimensions of size r. So here's our sphere curled up at each point in space-time, representing our 2 extra dimensions with the size capital R. And let's say we're measuring gravity on a scale of lowercase r. Well, we can't resolve this extra dimension, right? Okay, because we're the tightrope walker on the bridge here. We can't resolve that there's an extra dimension here. So if we measure the gravitational force at this distance scale, we're going to get the inverse square law, 1 over r squared. However, if we can be ingenious and devious and get to a scale that is smaller than the size of the extra dimension, like the ant on the Golden Gate Bridge, okay, then our gravitational force law will be 1 over r to the 4th. Okay? So you will no longer measure the traditional 1 over r squared. You'll see a modification or a deviation, and it will go with the number of extra dimensions. If there were 3 extra dimensions, it would be 1 over r to the 5th, and so forth. Okay? So this is what experiments do when they look for a modification of the gravitational force law, is they look for a different scaling with distance. So people build these really beautiful machines. They're very intricate and very small. It's a tabletop thing. There's several experiments, including one at Stanford. The apparatus is only about a foot tall, and it's torsion wheels. So here's a top torsion wheel, and here's a bottom torsion wheel. And they have different masses either cut out or attached to them. Here's, you can see on the top one, it's got holes in the top. And by rotating these torsion wheels in different directions, you can measure the force between the two wheels. And depending how accurately you've drilled these holes or put on the additional masses, you can get some measurement of the gravitational force law at small distances. There's obviously a technological limit here as to how closely we can measure this. And right now, the best limit on extra dimensions is sub-millimeters, 0.1 millimeters. Okay? But when you think about it, that's pretty big. Okay? 0.1 millimeters for an extra dimension is actually a pretty big. In fact, this is the size of these large extra dimensions. And the fact that this is the limit that we can probe in the laboratory tells us that we could have these large extra dimensional theories. Okay? The other thing I wanted to say about this experiment is that this is pretty much the limit of what we can do technically. Okay? So there's not going to be huge improvements here. And it's just a simple fact that with this type of apparatus, it's as sensitive as you can build it, basically. We're at the limit of, you know, drilling the holes. Okay. So how does this compare to Klein's prediction? Okay, remember Klein was the one who first made the prediction if you wanted to unify gravity and electromagnetism that the extra dimension had to be this small. Well, we're here, okay? So this is just, again, to emphasize, I don't want to say meaningless, how unrestrictive this experimental constraint actually is. We have very poor limits on the size of extra dimensions from this technique. And this is why extra dimensions could actually be big. Okay. Astrophysical limits. So you guys, you've got astrophysicists here, so you know about supernova. When stars burn up their fuel, they explode. They go supernova. When that happens, they expel a whole bunch of particles. If there are such things as Kaluza-Klein gravitons, okay, Kaluza-Klein particles, they will be expelled in the supernova as well as neutrinos and everything else. Okay? So these Kaluza-Klein particles would be ejected into the extra dimensions. So to us, the star or the supernova would be losing energy much faster than we anticipate from our standard solar model. Okay? Because if it's ejecting Kaluza-Klein particles and they're zipping off into the extra dimensions and not staying in our three-dimensional space, okay, then we don't see the energy that they carry off. They're carrying off energy, and to us, we don't see it. We can't measure it. So the supernova would cool much more rapidly than what we would anticipate. This puts a constraint on the size of the extra dimensions, and it's much better than that torsion wheel experiment, okay? You see, we're down here. We've got about 10 to the minus 8 centimeters, okay? For two extra dimensions. This is very dependent upon how many numbers of extra dimensions you have, okay? So it's very strong constraint for 2 extra dimensions, but if you have 6 or 7 extra dimensions, such as predicted by string theory, it turns out that this constraint washes out completely. The other thing to keep in mind about this is that our standard model of supernova explosions has a lot of assumptions associated with it. I mean, it's not like we can go to a supernova and stick an apparatus in there and measure it, okay? There's a lot of assumptions built in, so there's some play in this in terms of that as well. Nonetheless, you can get very strong constraints on the extra dimensions from astrophysical properties. They don't hold for the whole parameter space. They only hold for small numbers of extra dimensions, and they're very dependent upon our standard assumptions. Okay, colliders. Colliders are powerful microscopes. They make high-energy particles that allow us to see the small things. And the reason for that is because energy goes as 1 over distance. So the higher the energy you can accelerate a particle, the smaller the distance that you're probing. So that's the basic reason why we need particles at high energy, is so we can probe smaller and smaller distances. Okay? And this is just a pictorial example of that. If you have something like a proton that's actually made up out of quarks, you need a high enough energy beam to see the distances that small, to be able to resolve the quarks inside the proton. If you don't have enough energy, then the proton just looks like a point, okay, and you can't see the quarks. We also like to say they're time machines because they make the particles that are last seen in the earliest moments of the universe, okay? And when you take the two particle beams and collide them, then you have E equals mc squared. The particles will annihilate each other and create a burst of energy. And then you're able to produce new particles that haven't existed since the beginnings of the universe at a high energy scale. So we have one such collider, the Large Hadron Collider. So this is a proton-proton machine. It's going to accelerate protons. They'll explore energy regions that are a factor of 7 to 10 times our current highest energy accelerator, which is at Fermilab outside of Chicago. So the center of mass energy of this machine will be 14 TeV, hopefully. It was supposed to begin operation last September, and you probably have heard it was on for all of 9 days, and then they blew it up. Basically. So they're fixing it now. It's fixable. They'll fix it. It's just a matter of how long it'll take. Okay, so the current projection is that it'll be turned on again this September. Okay, so September of 2009. So it's a year delay. And they might not go up to the highest energies either, which is actually even worse. But it'll get there. It's the most complicated machine that humankind has ever built. It cost $8 billion, and the reason it was so cheap was because the tunnel existed already. We had used the tunnel for another accelerator, so $8 billion was actually cheap in that case. And it's not surprising at all that it would have some sort of glitch when it first comes on board. I've personally been waiting for this machine for 25 years, so another year doesn't faze me. But we're all terribly excited. So when it was turned on September 10th, we threw a party and stayed up till 3 o'clock in the morning. And I did a live blog of the event, and it was just really exciting. Okay, so there's 2 large detectors that are going to probe the high energy interactions. SLAC is a member of one of the collaborations. These are very early pictures of the detector. Sorry, I've got more recent pictures I meant to put in. This is Atlas here. It has a toroidal magnet system, which is what these little things are. And this is a CMS, which is the second detector. CMS was built in slices on the surface of the Earth and then lowered through a huge pit down into the accelerator ring. So that was a very scary time. The detectors are huge. Atlas is about 7,000 tons. There's a 4-story building at CERN, and it's as big as this 4-story building. Okay, it's huge. However, it's not very dense, and the claim is that it would float if you submerged it in water. And there's actually, this is out of date, there's actually about 2,000 collaborators right now on Atlas. Another collider I just want to mention, because it's something that's proposed that we want to build at some point, called the International Linear Collider. It would accelerate electrons and positrons and collide them and probe the same energy scales as the LHC. We would like to build this in the US, but it doesn't look like we're going to get funding for that. So maybe Japan. So how do you find extra dimensions at colliders? Well, now let's think about the brain world picture of extra dimensions. Here we are on the brain. Here's our incoming beams, okay, coming in each other, they're colliding. And it creates stuff, okay? So it's going to create some stuff that are particles that we know about and are trapped on our brain. And then it can create a Klein graviton, which then leaves our brain and starts propagating in the extra dimension. So just like in the supernova, this graviton is going to take energy away from the collision, okay? Or take energy away from what we measure. we don't see the graviton itself because it just flies off into the other dimension, so that's kind of hard to see. But what we can see is the energy that it carries away. We know the energy of the initial beams, okay? We can measure the energy of the stuff, the other stuff, okay, that comes out. And so just simple conservation of energy tells us how much energy this guy must have had, okay? So that's how we measure it. We actually don't see it, okay? So looking for particles that we can't see, this is a very tricky thing. It's looking for missing energy. There are lots of things that have missing energy in a collider. Neutrinos, okay, a standard model particle. We can't measure them in a detector either. They also have missing energy. Supersymmetry, you might have heard of supersymmetry. Its main signature is missing energy. So there's a lot of different possible things that can give you missing energy. It's a very tricky experiment to do. If your experiment has a crack in it somewhere, no matter how small, and an electron happens to sail through that crack and it doesn't get observed, then it's missing energy, okay? So there's a lot of things that can do. Nonetheless, this should have, if our theorists have calculated things correctly, this should have a very large amount of missing energy, and that's its signature. When we plot these things, we do Lego plots, this is called. So this is the detector unfolded. So if you just think like the detector being a can, like a can of tomato sauce or something, and you just unfold it, okay? And then you look at the amount of energy that was deposited along grids along the outside of this can. That's what a Lego plot is. And this is a simulation of graviton production where you have a very large tower of missing energy escaping one very small part of the detector. So this is the signature for graviton production. It's doable, but you're not going to do it the first day of the experiment. It's a very complicated thing. Okay, so that was one scenario. We have lots of different theories of extra dimensions. And so the other scenario, think of the brane world scenario where we're stuck on this membrane. Here the extra dimensions are curved, okay? So the graviton particles are actually real and spend some time in our three-dimensional space. And this is what it would look like if you mapped out the center of mass energy. You would see these bumps where each bump corresponds to another particle in the tower. Okay? So this is the easiest one to see because we actually have a bump in our detector. And if you get more than one, then you can actually do the mapping to see what this separation is, how wide is the peak, what does the dip look like here. All of these things give you information about the extra dimension. Okay, so that's the second main signature. So what can the LHC probe? Okay, they will set a limit or discover for 2 extra dimensions, basically 10 to the minus 4 centimeters, okay? And for 6 extra dimensions, it's much more powerful, okay? So this is still much bigger than Klein's prediction here, okay? However, it's exactly in the ballpark where these theories predict the stuff should be. Okay? So for once, for these theories with large extra dimensions that answer all of our questions, okay, if they really do answer our questions, okay, then they should exist within this region, and we should see them at the LHC, or exclude them if we don't see it. Okay. Last thing I'll mention is just to give you an idea about how we find out about the properties of extra dimensions. So this is just a production rate for graviton particles as a function of your center of mass energy. Okay? So if you have 7 extra dimensions, this is how the production rate maps out with energy. 6 extra dimensions looks like this. Okay? 2 through 7, they're all very distinct here. And the error on the measurement, which I've put here, this is the size of the measurement error. So just by mapping out the cross-section as a function of energy, this is why we need the E plus E minus machine, we can only do that there, we'll be able to tell you how many extra dimensions you have. Okay. So that's how. Yeah, this is GeV. And it's supposed to be femtobarns. Okay, so I told you this was a fun website. So anyway, even Einstein would agree that if we found extra dimensions, it would just profoundly change, just like if we find extraterrestrial life, it would profoundly change the way we view the universe, and we need to search for them and discover whether or not they exist.
Thank you. We have questions for our speaker. I'll use my prerogative to ask the first one. How would these extra dimensions relate to dark energy and dark matter? Could they help out with any of that? Or?
Absolutely. There's a lot of these theories where you put more than gravity out into the extra dimensional space. For instance, there's some of these theories where you put all of the standard model particles out into the extra dimensional space. And in that one in particular, the Klein particles of the photon can be dark matter. So what you need for dark matter is basically something that's stable. There's nothing, so there's got to be some sort of symmetry or property that there's nothing for it to decay into. And it needs to be neutral, no electric charge. And these theories have those particles in them naturally at the right energy scale where you can compute the relic density of the universe as measured by WMAP in degrees. Yeah.
In the last graph you showed where you had a whole bunch of different dimensions and different curves, there's a crossover point. What does that correspond to?
Oh, yeah. Sorry. This was just my normalization. I had to take some size of the extra dimension. Okay, so I picked a size for the extra dimension, and I picked a number of extra dimensions. So I picked a particular size and 2 extra dimensions, and that's what the cross-section would be at this point. And then given that size of the extra dimension, if it had different numbers, this is how it would map out. Yeah. But this is something, you'd be able to measure the size as well. I mean, that's something that's measurable too.
Between dimensions, are there quantum fluctuations, I would expect, if space is quantized? So do you get kind of a Hawking inertia or some kind of flux you can detect at the overlap between dimensions? And I have a part 2 to that.
Yeah. For these models of large extra dimensions, that's not as big of an effect just because the size of the extra dimension is so large. Quantum fluctuations are actually not that big a deal. Okay? But
Inertia or something like that.
no. No.
And also, I've always wondered about this. I've read about the string theory. Are the strings made of probability or what?
Well, the strings are matter.
Made of what, though? I mean,
Well, what's an electron made of?
strings. But
Strings.
that's the
Yeah,
point.
right. Okay, but right, it's the same thing. I mean, that's actually that's how I picture it. Anyways, I actually picture it as matter, as just like a piece of yarn. Only it's yeah. You could have that. It's like a duality thing. I think you could have that viewpoint. Yeah.
On the one graph where you had the gravitational forces, the electromagnetic forces, and the weak nuclear forces, and you were showing, okay, as they got unified with increasing energy, you'd get to the Big Bang. On the very bottom, you had a time bar that you didn't go over, I don't think. And
No.
I didn't reconcile the times on it, because it was like 10 to the minus 29 to the Big Bang, which isn't that more than what it really is?
There we go. So here's the time in seconds. So we actually don't have, this would be, well, obviously 0. So here we are at 10 to the minus 12, 10 to the minus 14, perhaps, seconds after the Big Bang.
Oh, that was okay. So that's
Is
time
that-
after the Big Bang.
Yeah. Sorry. Okay. I'm faster than this machine. So. Where were they? Come on, guys. There we go.
Oh, okay.
Yeah.
Well, I was wondering, the extra dimensions you were saying show up as mass, as one appearance of them, I guess?
Yeah, in our world.
In our world, right.
Yeah.
But a possibility that it could show up as an anomalous spin, angular momentum of some particle, or is that just not a possibility?
No.
No.
Yeah. And how can I explain that to you? They have their own angular momentum, okay? But they're not going to add any to a particle that already exists. So even if you had an electron that the extra dimension was small enough that the electron could be propagating in, and it doesn't change the properties of the electron as we see it, okay? It really looks like new particles rather than changing the properties of existing particles.
So the string would be the electron, so it would.
The string would be the electron, right? So for the so in this picture, the Klein particles. Well, all particles are different vibrations of strings, okay? And so the Klein particles are, because they're new particles, would be new vibrations of strings. Because in the string picture, all particles are just different vibrations of the string, right? So you just need to think of them as new particles.
Why a string when you go and zoom in I guess in your first approximation into that zoom, why not something else or some other configuration of?
Well, I think, okay, so let me give you a couple of answers here. One is simplicity, okay? You have a point object. The first thing you're going to try is extending it in one extra dimension, so that would be a string, versus extending it 12 different ways, okay? So it's simplicity. And so that's the first thing people tried, and it worked. They found a consistent theory, okay? So there hasn't really been any impetus to move beyond that, to something larger, because the string theory does provide a consistent theory of gravity, of quantum gravity. You know, if it didn't work, people might have gone on to higher dimensional objects, but it worked. Because it comes out within the mathematics to make the theory consistent, okay? Just to have an extended object in one extra dimension. The theory is mathematically consistent.
I guess you could have the object not being continuous, for instance, not.
I think you'd have problems with mathematical consistency then. Yeah.
Could one or more of the other dimensions would appear preferential to a particular particle or force?
Yes.
Such as, you know, the force is then kind of like a resistance or a conductance or permittivity or.
It wouldn't manifest itself quite in that way, but it is very possible that some of the forces can feel extra dimensions, but not all of them can. Okay, so you would have Klein particles for some of the forces, but not all of them. And if you got to energy scales where you could measure that force in the extra dimension, then the force law would change. So, yeah.
I really liked your ant metaphor there. Suppose the ants go down that cable in a spiral. To the tightrope walker, it would appear that an ant was going from one point to another without traversing the space in between.
Right.
Are there physical phenomena corresponding to that in this notion of higher dimensions or additional dimensions?
None that we have been able to observe to date. But that is another way of looking for it. And in fact, there's something that we're all very familiar with, and there's actual papers out on this now, believe it or not. It's called warp drive. That's why I'm able to talk about this. Yeah, right. Yeah, there are actual papers about going on a geodesic through a warp space, and right, and being able to hop through the dimension and travel through time faster, for example, or travel through, get through a longer distance faster. Okay. Okay.
Well, first of all, thank you very much for what may be the clearest talk on the planet on this complicated subject.
Thank you.
I have two questions, and I think you may have answered the first one a moment ago, but I'm going to ask it anyway. If gravity appears weak to us because it's spread out over all these other dimensions, why don't the other forces spread out in the same way and the ratio stays the same? The second question is, there's a very high energy tail to the cosmic ray distribution, which, if I remember right, goes up to like 100 TeV or something like that. Can you make any use of those collisions happening in the upper atmosphere to explore some of the physics here?
Let me answer your second one first. Yes. And in fact, I've got papers out on that. And it puts constraints on these theories that the Pierre Auger Observatory, which is sort of just turning on in Argentina now, should be able to probe the same energy region or distance scale, if you like, as the LHC in these models. Okay, so yes, gravity couples to energy, and so the higher energy you have, the better probe you have, and these cosmic rays have a lot of energy, obviously. Yeah.
That first question about
right.
the ratio of the forces.
Okay, so we don't have any good reason as to what particular force should be in what particular extra dimensions, if at all. Okay, there are models which will answer specific questions if you put specific forces in the extra dimension. The only thing that we know is that we haven't observed Klein particles of the particles we have. So that puts a limit onto the size of the extra dimension that the forces we know about can propagate in. There are models that put electromagnetism in a smaller number of extra dimensions than gravity, and a different size extra dimensions. I mean, this is a playground for theorists at the moment. Okay, and all of these theories are to address some sort of specific question that we're trying to answer, but there's nothing compelling, and we don't know. That's really going to be an experimental issue, and then we'll figure it out.
You've just explained to us very nicely why string theory has been called a theory unconstrained by data.
Yes.
Are you constrained to just space and time-like dimensions, and how do you tell what those other dimensions are, what types they are, and is there a third type, or,
Well, we only know about space and time, so it's really hard to conjecture about something else. I have an open mind, personally, and there could be something else, but experiment's going to have to tell me what it is, because I don't even know how to make it up. I don't know how to make it up. No. But there is a reason why we only talk about space. And that's if there's another time dimension, even though we'd all like more time, there's a mathematical problem in the fact that particles that would propagate in 2 time dimensions become tachyonic. Okay, so they have negative mass squareds. And that's a mathematical problem, and people have worked on it, and there's no good way around it yet.